Good morning, everybody. Welcome back to another episode of Science with Mr. Emond. Today we're going to be continuing on in our unit of heat, but we're going to be starting to look at something called latent heat. And latent is a word that means hidden. So we're looking at latent heat of fusion and latent heat of vaporization. Let's go through just reviewing the different states of matter, right? And how we go from one state to another. So we know, for example, that water can exist as solid, it can exist as liquid, and it can exist as gas. And we have different words for those, right? Ice, water, and steam. Whenever we're talking about something's melting point is the temperature at which something changes from a solid to a liquid. The boiling point is the temperature at which something changes from a liquid to gas. And these are words that we kind of know, melting and boiling. We also have freezing, right? Freezing is from liquid to solid. Condensation is from gas to liquid. Evaporation is from liquid to gas. And then we have words that you may not know, like going from solid all the way to gas, changing state from solid to gas. That's sublimation. And likewise, from gas to solid is sublimation. So you're skipping phases. Okay, so let's look at the heating curve for water. So I want you to notice, when we go from -20 to 0, this takes roughly 45 seconds, right? It's a fairly quick process here. But then what happens? The temperature doesn't keep increasing. There's this period of time that lasts for about 1 minute and 15 seconds where the ice stays at 0 degrees Celsius. It's not changing past the melting point. What's happening is the ice is actually melting in this phase. So despite actually adding in heat, because we're still heating up the water, the temperature of the ice isn't changing. It's just changing states. So that heat is being funneled into changing the state of the water from ice to a liquid. Okay? And that takes time and it takes energy. Once all of the water is in its liquid state, then you see we resume a temperature increase from 0 to 100. And once we get to 100, and you can kind of test this when you're boiling water or when you're cooking next time, check the temperature. The temperature doesn't keep increasing past 100 degrees Celsius, because what's happening is that liquid water is all the energy that you're adding to that liquid water to keep it at boiling point is being used to convert it from liquid to steam. And once all of the water is steam, then you can continue to increase the temperature of steam. And what we're focusing in on today is these areas, where the temperature remains static and all the heat that you're putting into the process is going towards changing state rather than increasing temperature. These are your latent heats, your hidden heats. Okay, so let's look at this. So when you add or remove heat, it doesn't always result in a change of temperature, and we saw that in these regions here. During a change of state, the heat that you add is called latent heat, which means there's no change in temperature and that heat is then hidden. We're still, one thing you have to remember, you're still adding heat to the system. You just can't see it on your temperature gauge. And that's why we call it hidden heat. And so this is something that we have to calculate for. And we have the latent heat of sublimation, the latent heat of vaporization, and the latent heat of fusion. Every time you change state, you need to be calculating the latent heat to change state. So latent heat of fusion, this is the amount of heat required to melt 1 kilogram of a substance, and we use this formula here. It's a very simple formula. Q, and remember Q is the symbol for heat, so the amount of thermal energy or heat required is equal to the mass in kilograms times the heat of fusion. And we have this chart here, which will be on Schoology 2, that has the heat of fusion and the heat of vaporization of a number of substances. And again, as a reminder, if we encounter problems that do not have the values here, just let me know and I will add them to this chart. This is an ongoing process because I'm changing a lot of the assignments. Latent heat of vaporization is the amount of heat required to vaporize, again, 1 kilogram of a substance. So this is a static quantity. However, the difference between fusion and vaporization is whether we're melting or vaporizing something, evaporating it. And you can see the formulas here are very similar. Q equals M, heat of vaporization, HV. And so just be very careful about whether you're looking for heat of fusion or heat of vaporization. And you will know which one you're doing based off what you're trying to do. If you're going from a solid to a liquid, which one's that? That's fusion. If you're going from a liquid to a gas, what's that? Vaporization. So just become aware of the differences between those because you want to be calculating them properly, using the right H values, latent heat values. And then just as an understanding, why is this occurring? All that energy, that latent heat, that latent thermal energy that goes in, what is it actually doing? It's trying to overcome the electromagnetic forces that are holding those atoms together, right? Remember that solids are held very closely, very strongly together, and that heat that we add breaks them apart so that they're more free-flowing into a liquid state, and likewise into a gaseous state. All right, so here's your heat of fusion and heat of vaporization for a number of compounds. We also don't want to forget this, your specific heat capacities. Because when you're changing state, when you're in, remember we had a curve, right? Going from increasing temperature to changing state to increasing temperature. Whenever you are on this part, an increasing part, this is your specific heat capacity. Right? You're looking for a change in energy and you're using your specific heat capacity. So change in temperature, and we had that formula from yesterday, mass, change in temperature, and specific heat. That's going to tell us how much energy is required to do this. Once we get to a region with latent heat, it changes a little bit, right? So once we're at this plateaued region, this is where we calculate our latent heat using our heat of fusion and heat of vaporization. So you're going to notice these become kind of multi-step problems now. Problems that I know you guys love to do when there's 4 or 5 different steps to answer the same question. All right, so let's go ahead and try a problem out. How much heat energy is needed to change 2 kgs of ice at 0 degrees Celsius into water at 0 degrees Celsius? So all we're doing here is a change of state, and we're changing our state from ice to water. So we're starting with ice at 0 degrees Celsius, and we're going into water at 0 degrees Celsius. So this is from a solid state to a liquid state. When we go from a solid to a liquid, this is fusion. So we are going to be using this formula for the latent heat using the heat of fusion. So let's get started. We have Q equals the mass is 2.0 kgs, and we need to multiply it by the heat of fusion of water. So let's go back here. Heat of fusion of water is 3.3 times 10 to the 5. So times 3.3 times 10 to the 5. And this is, sorry, not kilograms, 3.3 times 10 to the 5 joules per kilogram. And you can see what's going to happen here with our digits is our kilograms are going to cancel out, leaving us with just joules, and that's good because heat is measured in joules. So now all we need to do is go to our calculator here. So we are going to start a new document, and we are going to solve. So 3.3 times 10 to the 5 times 2 is 660,000. Okay, and this is joules. Now we want to be careful. We have two significant digits. So we're going to say Q is equal to 6.6 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5 joules. And that is our final answer. So that's pretty easy. Let's try another one. Okay, so for this problem, we're going to be trying to find out how much heat energy is needed to change 0.50 kilograms of water at 100 degrees Celsius into steam at 110 degrees Celsius. So let's kind of visualize what's happening here. So we have H2O, and it's at 100 degrees Celsius. We're going to have to change it into steam. Now this is H2O as a liquid, right? We're going to change it into H2O as a gas, and it's still going to be at 100 degrees Celsius. And then we're going to increase the temperature. So it's still going to be a gas, but we're going to increase the temperature to 110 degrees Celsius. So there's two things that are going to be happening here. The first thing is we're going to change states. So this is going to be our heat of vaporization. Our second thing is going to be increasing temperature. So let's start off with step 1. Now, one thing to note is there's heat of fusion and there's heat of vaporization. These are two different things. The difference between them: fusion is what happens when you go from a solid to a liquid, or a liquid to a gas. Or solid to a liquid, or a liquid to a solid, sorry. So it's changing states from solid to liquid in either direction. Heat of vaporization, just think about what a vapor is. A vapor is something that has evaporated, right? And so that's any time we're going between the states of liquid and gas would be your heat of vaporization. This case, we're going from liquid to gas. So which one is it? Heat of vaporization. So we are wanting to use the formula Q equals mHV. Let's start plugging in numbers. So we have 0.50 kilograms, and the heat of vaporization, we need to go back to our table. Heat of vaporization of water is 2.3 times 10 to the 6. So it's 2.3 times 10 to the 6, and this is joules for every kilogram. And at this point, you just plug this into your calculator. So let's do that. You have 2.3 times 10 to the 6, which is quite a large number, times 0.5. And that's going to give you 1.15 million joules. And we want it to be at 2 sig figs. And so our answer here is going to be 1.2 times 10 to the 6 joules, right? 1, 2, 3, 4, 5, 6. Excellent. Okay, step 2. What is step 2? We're actually changing temperature this time. So anytime you're changing temperature, and we can see we're going from 100 to 110, you're going to use the formula that actually has a change of temperature in it. And it doesn't matter if you're never going to be changing states. You're just changing temperature. The one thing that you have to watch is the C value, because your specific heat capacities, of course, are going to be dependent on what state you're in. So let's plug in our numbers. The mass is still the same, you're not going to be losing any mass at any point along the process, because matter cannot be created or destroyed. So we are going to be at 0.50 kilograms still. Our specific heat capacity of water, we want to watch the state. This is a gaseous state. So we're going to go to our specific heat capacities for water, and we are looking for the gaseous state, which is 2.0 times 10 to the 3. So 2.0 times 10 to the 3. And of course, this is joules per kilogram Celsius. And finally, we need our temperature change. Our final temperature is 110. Our initial temperature is 100. 110 minus 100 is 10 degrees Celsius. Okay, let's plug these values in. So we have 2.0 times 10 to the 3. We are going to multiply that by 0.5, which is 1,000, and then multiply that by 10, which is 10,000. And this is joules. And of course, when we look at this number, it looks like we only have one significant digit, but really we're limited by 2. And that's why you're going to write this in scientific notation. Always write it in scientific notation, because that's the quickest way to know exactly how many significant digits you have, and also have a little bit of information about how accurate or precise these measurements are, right? We're not sure about these digits in reality. So 1, 2, 3, 4 times 10 to the 4 joules, and there's our answer for step 2. Now for the final step, we're looking at how much energy is needed to do the whole process, right? So for the whole process, which is going to be, let's call it step 3, we're actually going to be adding them together. So you're going to have 1.15 million, and of course we're going to use these because they have just a few more digits. We're going to remember that really they're limited by 2. Right? So 10,000 here. And that is going to be, so let's throw it in our calculator. That 2 significant digits is, and notice we didn't actually change the number very much, right? It's still 1.2 times 10 to the 6 joules. That's kind of funny. And that's because we're limited by significant digits, right? So this step, and I should probably have put a box around that. Our answer for step 1 is the same as our answer for step 2. And that's because this one was a negligible amount of heat in comparison to the amount of heat needed to change it from a gas into, our liquid into a gas. This required a ton of heat. And then once we actually were in the gaseous state, to increase by 10 degrees Celsius, not a big deal, not very much heat going on there. So our final answer is actually the same as in step 1 because this was negligible. Let's move on. Your turn. So give this a shot. How much heat does a refrigerator need to remove from 1 kilogram of water at 20 degrees Celsius to make ice at 0? So you're going from 20 degrees to 0. And you're trying to make ice. So there's going to be a change of state as well. Go ahead and pause the video now and come back when you think you have your solution and we'll go over it. See you soon. Okay, for those of you on YouTube, welcome back. We have the solution for you. So let's go through it. The first thing we did is we set up our chain of events. So we're going from 20 degrees Celsius of liquid water, and we're changing it into 0 degrees Celsius of liquid water. So this is going to be our step 1. And then we're taking this 0 degrees Celsius liquid water and we're changing it into solid water. And that's going to be our step 2. So for step 1, because we're not changing states, we're just decreasing temperature, you use Q equals MC delta T. And you take your givens, and so we're dropping by 20 degrees Celsius and the other stuff is given to us. And all you do is you plug it in. It's no big deal. You plug it into your formula and you would find Q equals negative 125,400. And now we just put it in scientific notation with the right number of significant figures. And so negative 1.3 times 10 to the 5 joules. That's step 1. For step 2, you're using your heat of fusion. And so you're using this formula. And again, it's the same mass heat of fusion you get from your table. And you plug it into your formula and you find Q equals 495,000. Now, one thing that I bet a lot of you did is you didn't remember that we're actually going to be removing energy here. And when you are removing energy from the system, that should be a negative value. So logic and intuition should be able to help you realize that this should be a negative value. Even though it's not a negative mass and your heat of fusion is a positive number, this in the end should be negative because we're removing that heat. And so once you put it in scientific notation, it's negative 5.0 times 10 to the 5 joules. We add the two together to find our total amount of heat required. And that total amount of heat was negative 620,400 joules. And then of course, put it in scientific notation and it's negative 6.2 times 10 to the 5 joules. That is it. Let's do one final question. This is the big kahuna of the day. It is not an easy problem. It's a level 4 problem, and it's a multi-stepper. And so I've kind of already broken it down into its stages for you just to try to make it a little bit easier. But this is the easiest step, I think, is doing a visualization process of where you have to go. So the question was, how much heat is lost from 1.5 kilograms of steam? So we're starting off as steam, and it's 135 degrees, and we need to go all the way to negative 17. So the chain of events is go from steam at 135 to steam at 100. Then we change states from steam to water. Then we change states from water, not change states. Then we change temperatures from 100 to 0. Then we change states from water to ice. Then we change temperatures from 0 to negative 17. And so each of these arrows represents a step. So how many steps is your problem going to have? A whole whack of them. Step 1, step 2, step 3, step 4, step 5. This is a level 4 question for a reason. It demonstrates mastery of the topic. We're winding down to the end of the unit 2, the first unit of heat. So this is, if you can get this, you are in excellent shape. Here's all the formulas that you need. You need your formula for calculating changes of temperature. You need a formula for the heat of vaporization. Remember, vaporization is when you go from a gas to a liquid or from a liquid to a gas. So that's what you use for some of these steps. And you need your heat of fusions for going from solid to liquid or liquid to solid. Give it a shot. I'm going to give you guys time, at least probably 10 minutes to work on this, I would say. And I will be back for those of you on YouTube. Pause the video, work it out, and we'll see you then. All right, welcome back. We have the solution for you. So for step 1, we're changing temperature. So we're going to use Q equals MC delta T. And all you're going to do is you're going to plug in your values. That's it, and solve for Q. It's going to be a negative number, obviously, because we're decreasing temperature. So negative 1.1 times 10 to the 5 was step 1 here in blue. Step 2 in purple, we're not changing temperature. This time we're using our latent heat formula, and we're going from steam, which is a gas, to water, which is a liquid. So that means we're going to be doing heat of vaporization. So this is going to be your Q equals mHV. Plug in your numbers. So 2.3 times 10 to the 6 was the heat of vaporization of water. And you will find Q is negative 3.5 times 10 to the 6. Step 3, we're changing temperatures from liquid water to at 100 to liquid water at 0. So Q equals mc delta T again. Plug in your values. This one is going to end up giving you negative 6.3 times 10 to the 5. Step 4 in green. Step 4 is changing state from liquid to solid. Liquid to solid is your heat of fusion. We're fusing there. And so we're using Q equals mHF. Plug in your values. You will find it to be negative 5.0 times 10 to the 5 joules. Now, one thing to remember is, despite the fact that these are both positive numbers, just like in the previous examples, we know that we're going in the negative direction, right? Because we're removing energy. So these values need to be negative. We need to remember that. Step 5 in orange, we're decreasing temperature of ice. So solid water to ice with negative 17 degrees Celsius. So again, this is our Q equals mc delta T. Plug in your values and you will find Q is negative 5.4 times 10 to the 4. Now, one thing to remember is, for all these times that we were changing temperature, we were using the specific heat capacity of water. But the specific heat capacity of water depends on the state. So this one is as a gas, right? 2.0 times 10 to the 3. This one is as a liquid, 4.18 times 10 to the 3. And this one is as a solid, 2.1 times 10 to the 3. So be careful with your states of matter. They're going to make a big difference on your final answer. And finally, for the total amount of heat that's required to do this whole process, well, you've got to go and add them all together. They all should be negative values, because every step of the way we're losing heat energy, we're losing thermal energy. And so our total net loss is going to be negative 4.7 million, or negative 4.7 times 10 to the 6. Two significant digits, because in our original problem we were multiplying mass in all of these, and with our mass we only had two significant digits. That's it for today. Thanks for watching. See you next time. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here you will find the next video in this unit. Keep learning, everybody. Take care.